this is section 3.8, and this section covers boundary value problems. And just like the previous sections, we want to solve differential equations that are linear. That means the degree of y or y double prime, or maybe you have something like that, the degree of y prime is 1, so that's why they're linear. They're homogeneous because they're equal to 0, and they are second order differential equations. And we call them boundary value problem because we are going to have maybe the value of the function at 2 points, or maybe we have the value of the derivative of the function at 2 points, or maybe the combination, the value of the function and the value of the derivative of the function at another point. So they're slightly different than initial value problems. With initial value problem, you would have y of a is equal to a number, and then y prime of a is also equal to another number. So these are initial value problems, but we have boundary value problems where we have 2 points. We have the value of the function or the derivative of the function at 2 different points. And these 2 points, if they are the beginning and end of the domain of the function, then we have endpoint boundary value problem. But if a and b are just within the domain, then we have a boundary value problems. So we just want to learn how to solve them. They're more complex than initial value problems. So what I want to demonstrate is an example from your homework. Let's say we have x double prime, or let me just use y double prime plus 4y is equal to 0, and we have y of 0 is equal to 1, and y of pi is also equal to 1. So we want to solve the boundary value problem. And we are going to solve this differential equation using substitution. I'm going to guess that y is ERT, find y prime. I get r ERT because we find derivative of ERT. T is the independent variable, so derivative of ERT is ERT times derivative of the exponent, which is just r. Then we find y double prime, which is going to be another r ERT, so that makes it r squared ERT. And then we substitute them. We substitute this here, we substitute this one here, but since we have 0 on the other side, we can just drop the ERTs. So we end up with r to the power 2 plus 4 is equal to 0. We isolate r by moving 4 to the other side and finding the square root. So we get r is positive negative 2i. So then, if this is our solution to R, then the differential equation, solution is going to be y of t, or y of x, y of t because I use variable t, is equal to C1 cosine of this 2t plus C2 sine of 2t. Now I am going to use the boundary value that are given to me. Substitute 0 for t. Y of 0 is 1, so that's 1. C1, 2 times 0 is 0. Cosine of 0 is 1. 2 times 0 is 0. Sine of 0 is 0 times C2, I get 0. So I get 1 is equal to C1. Next, we are going to evaluate. So I have C1 is 1. I want to use the other value of y. Y of pi is equal to C1 cosine of 2 pi plus C2 sine of 2 pi. Sine of 2 pi is 0. Cosine of 2 pi is 1. C1 is 1. And y pi is 1. So I get 1 is equal to 1 times 1 plus 0, which shows 1 is equal to 1. So this implies that C1 is 1, but C2 can be any number. So therefore, the solution y of t is equal to cosine 2t plus C2 can be any number, sine of 2t. So therefore, we have infinitely many solutions. Now, I want to show you another example. Let's say I have y double prime plus 4y is equal to 0. And we have y of negative pi, or y of 0 is 0, and y of pi is 0. So we call this endpoint boundary problems because you have 0 here, 0 here, and this is a homogeneous second degree linear differential equation. And we want to find a solution to this equation. So what we have to do is we are going to use the exact substitution as we have here, the same solution here and here. So everything is going to be the same as above. So we know that y of t is going to be C1 cosine 2t plus C2 sine 2t. And then we are going to substitute 0 this time. We get C1 cosine of 2 times 0 plus C2 sine of 2 times 0. Again, sine of 0 is 0. So, and cosine of 0 is 1. And y of 0 is 0. So we get 0 is equal to C1. We have y of pi is equal to C1 cosine of, I'm doing this right now, I'm substituting pi. I substitute a 0 and then I substitute pi for t. Sine of 2 pi is 0. Cosine of 2 pi is 1. And this is 0. So again, I get 0 is equal to C1. I'm just going to go ahead and substitute 0 for C1. So what in either this equation or this one. So I'm just going to go to this equation. I say y of pi, which is equal to 0. And C1 is 0. And then I have a cosine of 2 pi plus I have C2 I don't want to go here. I apologize. I'm just going to, I just get C1 is equal to 0, but I don't know what C2 is going to be, because I was going to substitute 0 here. I would get 0 is equal to 0. So that doesn't do me any good. So what I want to do here is I want to, what I want to do here is just go back to the equation, to the solution, substitute 0 for C1, but I wasn't able to find C2, so therefore C2 could be any number. 0 times cosine of 2t is going to be 0. So therefore y of t is equal to C2 cosine sine of 2t. And C2 could be any number. So again, I have infinitely many solutions. What I want to explain to you here is that this 4 is called lambda, and it is called eigenvalue. So 4 is called an eigenvalue. Why is it called an eigenvalue? Because I get y of t is equal to C2 sine of 2t, which is also has a name. It is called the eigen function. So anytime you can find a number here, a coefficient for that y, in such a way that you get infinitely many solutions, like this case, that I got infinitely many solutions, then we call that number here an eigenvalue, and we call this one the eigenfunction. So I want to go over, write down a definition. So let's say I have y, I have y double prime plus lambda y is equal to 0. And then I have y of 0 is equal to 0. And y of pi is equal to 0. So pretty much I wrote the same equation, only instead of 4, I said, let this be a lambda. I want to see if I can find an eigenvalue or eigenvalues that satisfies this equation. I want to find a lambda so that I will get infinitely many solutions for my differential equation. Therefore, then we call those solutions eigenfunctions. So I want to find eigenvalues, lambdas, that give infinitely many solutions to this differential equation. And those solutions are called eigenfunctions. So how do I find such a lambda? I'm just going to use the same substitution as before. This becomes r to the power 2. This is only lambda is equal to 0. So again, I just use this substitution. This is what we get. I want to isolate r squared. The square root both sides. And this is what I get. Then therefore my solution, yt, is going to be C1 cosine square root of, I dropped the square root here, I apologize, there's the square root of lambda t plus C2 sine square root of lambda t. So remember, I want to find a lambda or lambdas, eigenvalues, that is going to give me infinitely many solutions to this differential equation. So how do I find them? I'm just going to use the value of the function at 0. So y of 0 is 0. 0 times lambda is 0. Cosine of 0 is 1. Square root of lambda times 0 is 0. Sine of 0 is 0. I guess 0 is equal to C1. Then I'm going to substitute pi. So then I already know C1 is 0, so I'm just going to put it here. Y at pi is 0, C1 is 0. So this will be 0. This is what I get. So I want to solve this equation. This equation has two factors. C2 is a factor, and sine the square root of lambda pi is a factor. So either C2 has to be 0 for me to get a 0 here, or sine of the square root of lambda pi has to be 0. So I already know C1 is 0. If C1 is equal to 0 and C2 is equal to 0, then what we get is we get trivial solution. Because then y is going to be 0. So if C1 is equal to 0, having C1 is 0, and then having C2 is equal to 0, then I get y is equal to 0, which is a trivial solution. If sine of the square root of lambda pi is equal to 0, then we want to solve this. So the square root of lambda pi is equal to inverse sine of 0. Inverse sine of 0 is going to equal to n pi. So if you put this in your calculator, it's just going to give you 0. But you know that sine is a periodic function. Sine is 0 at angle 0. At angle pi is 0. At angle negative pi is 0. If I go 1 pi and 2 pi is going to be 0. At 3 pi is going to be 0. At 4 pi is going to be 0, and so forth. So at all the multiples of pi is going to be 0. Pi and pi cancel each other. I get a square root of lambda equals to n. Square both sides. I get lambda is n to the power 2. So if I substitute this back in here in this equation, I get C2, because now C2 can be any number. Sine of the square root of lambda, and the square root of lambda is n squared. And then I have t. So that gives me C2 sine of nt equals to y of t. 4 was one of those numbers. So if lambda is equal to 4, then I have the above equation. It's the previous example where I solved. And then we got the same outcome, only here I have sine of nt. So in other words, if this is equal to 9, that's also a possibility. If I change this to any other number, then this n is just going to change accordingly. But then right now we call these eigen values. 4 is one of them, 9 is another one of them, and then this other one, yt, is called the eigenfunction.